This video describes the machining of new Delrin roller bearing sleeves for the Accu-Slice system to improve the performance and accuracy of the carriages on the Accu-Slice system. Hello, I'm John Manier from Accu-Slice. In this video I'm going to be machining these Delrin roller bearing sleeves for the Accu-Slice system. I'll be using the Fusion 360 software to design the roller bearing sleeve and also to generate the G-code, which is used to program the Tormac 8L lathe using a gang tooling which I developed and described in a previous video. The standard roller bearings for our Accu-Slice system consist of two stainless steel ball bearings with a polycarbonate outer sleeve or covering. These roller bearings are used on various carriages and accessories for the Accu-Slice system to enable them to ride smoothly on a linear rail. Similar roller bearings are used on linear actuators, XY plotters, CNC routers, and other linear motion systems. We've been using these roller bearings with these polycarbonate outer coverings for more than 7 years for our Accu-Slice system. But on occasion we've seen these polycarbonate coverings deteriorate and crack over time. This cracking normally occurs due to excessive pressure between the roller bearings and the rail on which they travel. Excessive sawdust buildup on the roller bearings also causes premature wear or cracking of the polycarbonate coverings. I've been investigating alternate materials for the sleeves or coverings for these roller bearings to see if they can be improved. I've discovered that Delrin may be a better option. In my initial testing of the Delrin roller bearings, I have seen improved performance of the roller bearings. They ride more smoothly on the rail, and I have seen no evidence of any cracking of the roller bearings. As a result, I do believe that these Delrin sleeves will provide for improved performance on our Accu-Slice system. I'll be using the Fusion 360 software to design the Delrin roller bearing sleeves and also to generate the G-code for the CNC lathe machining. On the design screen, I drew the cross-section profile of the roller bearing sleeve. I took these dimensions from the original drawing of the polycarbonate sleeves that we previously used for the Accu-Slice system. There are a couple of items to note from this drawing. The depth of the two recesses into which the roller bearings will be inserted are not symmetrical to one another. The roller bearing on the left side will be recessed 0.220 inches into the sleeve, and the other bearing will be recessed 0.188 inches into the sleeve. This offsetting of the two bearings is important to remember when the finished roller bearings are installed into the carriages on the Accu-Slice system. The 0.030 inch spacer between the two roller bearings is where we will eventually add a small steel washer to separate the two ball bearings. From this cross-sectional drawing, I then rotated or extruded this cross-section profile around the bottom axis to get the finished image of the roller bearing sleeve. You can still see the line image of the cross-section that I just created, which I will then turn off. Rotating the image demonstrates the complete 3D profile of the roller bearing sleeve. Next, I can add the two roller bearings to the Delrin sleeve to show how they fit. As I rotate the image, notice that the outer surface of one of the roller bearings is slightly recessed into the sleeve, while the second roller bearing outer surface is flush with the side edge of the sleeve. From this 3D representation, I can next create the schematic drawing and add the critical dimensions that I will need to check when I start to actually machine these roller bearing sleeves. As I begin to machine these roller bearing sleeves, there are a number of critical dimensions that I'll need to monitor. The dimensions that I need to be checking will first of all be the diameter of the two recesses for the roller bearings. Since I want a very tight fit of the roller bearings into the sleeves, this inner diameter must be slightly less than the outer diameter of the roller bearings. The roller bearings measure 0.500 inches in diameter. Therefore, my dimensions for the two recesses for these roller bearings must be 0.4995 inches, which will provide a very tight fit for the roller bearings. As I machine these roller bearing sleeves, I will periodically check this tight fitting by inserting the roller bearings into the recesses to make sure that they are held tightly, but not too tight to the point that it will be very difficult to press the bearings in place. The other two dimensions that I will periodically be checking are the depths of the two recesses for the roller bearings. One recess is 0.220 inches deep, and the second recess is 0.188 inches deep. The other dimensions will also be checked. Now I'm ready to create the G-code from which I will machine these roller bearing sleeves. I'm using a 3/4 inch diameter Delrin rod produce these roller bearing sleeves. I will be machining these sleeves on my Tormek 8L lathe using the gang tooling that I developed and demonstrated in a previous video. Since I'm using a 3/4 inch round stock, I'm limited to using 4 turning tools on the lathe. Since I need to machine about 300 of these items, I want the lathe to run uninterrupted with no manual tool changes. I was originally planning on using 5 tools on the lathe, but there just was not enough space between the tools. So I'll be using the following 4 lathe tools. I determined I could use the parting tool to both face off the front surface of the sleeves and also part off the back surface. I'll be using the front tool post for general profiling of the outer surface. The other 2 tools I need will be a 3/8 inch diameter drill to drill the center hole and an internal square tip grooving tool to produce the profile for the 2 inner recesses for the roller bearings. The grooving tool is a special square tip grooving tool with a 5/16 inch diameter shaft, which required me to generate a custom tool profile in Fusion 360. The machining of the sleeves required 7 separate tooling programs. The first step used the rear parting tool to face off the front surface of the 3/4 inch diameter Delrin rod. The second step used a 3/8 inch diameter drill to drill the center hole in the Delrin rod. Step 3 uses the grooving tool to machine the .220 inch deep recess for the first roller bearing. Step 4 uses the same tool to machine the back .188 inch deep recess for the second roller bearing. Steps 5 and 6 use the general finishing tool on the front tool post to machine the outer profile of the sleeve. Step 7 once again uses the rear parting tool to part off the sleeve to its finished length. Here is a simulation of all 7 operations. The rear parting tool first of all faces off the front surface of the piece. Then the 3/8 inch drill drills the center hole. To machine the inner recessed openings for the ball bearings, we're using a multi-step pecking operation to clear away the bulk of the inner surface material. A linear smoothing pass of the tool cleans up the surface to provide a smooth, clean finish. The front profiling tool generates the outside profile of the sleeve. Again, this is a multi-step machining process with a finishing pass that provides for a smooth outside surface. The parting tool cuts off the sleeve to its required length. Finally, I used the Fusion 360 software to generate the G-code to machine these Delrin roller bearing sleeves on my Tormek 8L lathe. There were a number of manual edits that I needed to make to the G-code for it to operate properly. Since the parting tool is on the rear tool post on the lathe, I reversed the X position values for the facing and parting code lines. Second, since I want the lathe to run uninterrupted, I commented out any tool stop and spindle stop lines in the code. These changes allowed the lathe to run uninterrupted through all the tool changes with no operator involvement. By making these changes, I was able to get the total machining time down to 2 minutes per piece. I then transferred this G-code to a memory stick and installed it into my Tormek 8L lathe. These images show the 4 tools mounted on the Tormek 8L lathe gang tooling plate. On the far left, on the left tool post, is a parting tool, which will be used to face off the front of the Delrin bar and also cut off the final length of the sleeve. Next to that is a 3/8 inch drill, then the flat tip grooving tool, and on the far right is the profiling tool mounted on the front tool post. Since I'm machining a 3/4 inch diameter round bar, which is a black bar with a blue text, the clearance between all the tools and stock is quite close. In some cases, the clearance between the tool and the stock material was less than 1/4 inch. It took me a little while to properly position all the tools on the gang tooling plate, and even some minor modification of the G-code previously described to get everything properly aligned so there's no collision between any of the tools and 3/4 inch stock. Since I'm not using any coolant, I did operate the lathe with the top cover open during all the turning operations. I did add an air sprayer to blow away some of the Delrin turnings as they were being machined. I did later modify this for improved removal of the turnings for the grooving tool to keep it cleaner. All the tools were all set for perfect alignment to achieve the required accuracy for the dimensions required for this project. On several occasions, I readjusted the offsets for the grooving tool to get an accurate dimension of the recessed grooves for the roller bearings. Here's the actual machining of one of the Delrin roller bearing sleeves. It is being shown in real time since the total machining time is only about 2 minutes. First, the rear parting tool faces off the front surface of the Delrin bar. Then a 3/8 inch drill drilling the center hole for the bearing sleeve. Next, the flat tip grooving tool profiles the recess for the first ball bearing. This is a multi-step machining process to machine the inner grooves for the ball bearing. First, a pecking motion is used to clear away the bulk of the material. Then a final cleanup pass is run to smooth out this inner surface. Then it moves further into the bar to profile the rear ball bearing recess. The same multi-step process of using the pecking steps to clear away the bulk of the material, followed up with a cleanup step to smooth out the inner surface for the second ball bearing. I later modified this step to do a better process of clearing away the filings that were accumulating at the Delrin bar. By clearing away these filings, I was able to get a cleaner inner surface. Next, the profiling tool cuts the shape of the outer sleeve. Several passes were made to achieve a smooth surface. Finally, the rear parting tool cuts off the sleeve to its required length. And here's the second piece being machined at a slightly different camera angle. This part of the video is being shot at 5 times the actual cutting speed. And here is a finished Delrin roller bearing sleeve, shown at 2 different angles. I just want to show the replacement of the roller bearings on an existing Accu-Slice carriage, or it could be an Accu-Slice wedge, either one. And on this particular carriage, there's 3 roller bearings. This front one's the adjustable bearing, and then there's 2 in the back which are stationary. And these have been on here for probably about 5 years. They're not cracked, but there's a lot of pitting in the surface from sawdust getting caught between the roller bearings and the rail. And that's on this 45-degree angled surface. That's what gives the pressure to tighten it against the rail. So the first thing is to remove the roller bearings. And this top one here is the adjustable one. I have a brass offset cam on one side. And so just remove that. And I can move the roller bearing. And I can leave that in place and just put the new roller bearing on. Now it's very important that the side with the recess faces out and the flat side faces down. That goes under like that, and then I put the screw to tighten it in place. And this will need to be adjusted on the bands on the rail. And when you're done, there should be a small gap between the roller bearing and the stainless steel or aluminum offset piece at the bottom. So there should be a visible gap between those two. If there's no gap, it's going to bind and this wheel will not turn. So likewise, I can replace the other 2 bearings. And these are stationary. And there's a lot of pitting on that. So again, the same process. The recessed area sticks up such that there's a gap a visible gap between the roller bearing and the stainless steel offset spacer. These get tightened down pretty good. Make sure they turn freely. If it doesn't turn freely, it's because you got the roller bearing on upside down. And if you do get one of these roller bearings turned upside down, when you go and put it on the rail, you're going to get a very rough movement. It's going to be real hard to move. So it'll be visibly easy to see that problem. But again, there's a gap between the two. And then we take it over to the rail in the Accu-Slice system and adjust this offset cam to get the correct tightness. You want these to ride fairly tightly on the rail, but not too tight. You don't want any wobble in the system. So you adjust this to get tight. There's no wobble, but yet it slides fairly easily. I've shown this in previous videos, but I'll repeat it here again. That's how to adjust this brass offset cam so that the carriage rides properly on the rail. And in this case, this is my 12-inch carriage. There's one of these brass offset cams. On a 24-inch carriage and the 30-inch carriages, there's two of these that need to be adjusted. These are fixed, but this one rotates. So when you first put it on your system, it may not fit. You may not be able to put it on. That's because this is incorrectly set. So you may have to loosen this up so that it fits. But I got mine pretty loose now. You see a lot of wobble and play in this. And that needs to be adjusted by turning this brass offset cam. And I can turn this till the play goes away. See, that play's gone away now. And if I turn it too much, it actually tightens so much that I can hardly move the carriage. So that's too tight. So you want to adjust it such that the play is eliminated, but it slides fairly smoothly on the rail. But you don't want it too loose. You don't want it so that it just would fly off the end of the rail to do that. You want it a little bit tighter than that. You want it like that it slides but stops. That way it'll be minimal play in this and you'll get nice surfaces on your boards. Now after you get that set, then you go to the bottom and tighten this bottom screw. Now when you do that, it's going to get tighter. So I may have to actually go back and loosen this up a hair. It's still a little too tight. That's pretty good. You can see the roller bearing should be rotating. And then when I go back and double check it once again, double tighten that bottom screw. And again, tighten it up a little bit more, so let me loosen it a hair. And just double check the tightness. So that's pretty good. The roller bearing is actually rotating quite nicely. It rides pretty smoothly, but doesn't ride too freely. And I've used two Allen drivers, an 1/8 inch for the bottom and a 3/16 inch for the top. These roller bearings are used on my Accu-Slice system, both on my normal carriages for the Accu-Slice system and also on my Accu-Wedge. This is my Accu-Wedge I've been using now for about 5 years. And I did replace the roller bearings on this Accu-Wedge. The original bearings that were on there for like maybe 5 years are still in good shape. There's no cracking on it. But there is a lot of pit marks in the surface of these. And I can feel that a little bit as they ride on the rail. And these typically ride on the rail, right on both sides of the rail. So I did replace them on my Accu-Wedge carriage. You see I replaced all 4 of them. I've been using these now for about 2 weeks. And they're in great shape. They definitely ride smoother on the rail. There's no pit marks on these. And when I put this on the rail, it definitely rides a lot smoother. I mean, that's nice and smooth now. I just installed 2 carriages on my Accu-Slice system. And these are 2 brand new carriages, never been used in the past. On this one on the right, I have my polycarbonate roller bearings. And on the left here, I have my carriage with the Delrin roller bearings. And this Delrin definitely runs smoother than the polycarbonate. And it's definitely a little bit quieter. But as far as smoothness, there's definitely a difference. So in conclusion, I recommend if you need to change your roller bearings on your system, if they're starting to get clogged up and running a little bit rough, I recommend using the Delrin roller bearings. It's a definite improvement for the system. This project took me about 5 days in total. I'm still a novice to using Fusion 360, so I spent almost 2 full days programming this project and further learning the software. I spent about half a day setting up and adjusting the lathe tools so that everything worked perfectly. I was able to get the total machining time down to 2 minutes and 7 seconds per piece turned on the lathe. And it takes me another 30 seconds to set up for the next piece to be turned and inspect the finished sleeve for accuracy. Over a period of 2 days, I machined a total of 300 of these Delrin roller bearing sleeves. I was quite pleased with the finished roller bearing sleeves. The machining was quite accurate. When I inserted the roller bearings into the sleeves, they fit quite snugly, and the finished project worked quite perfectly. If you want to upgrade or replace the roller bearings on your Accu-Slice Carriages or Accu-Wedge, the Delrin roller bearings are available on our website. The part number is AS4000DR and includes a new Delrin roller bearing sleeve with 2 stainless steel roller bearings installed. Thank you for watching this video. If you have any questions, concerns, or comments, as always, please give us a call or drop us an email. Thank you for watching.